Okay, so welcome back to this section 4.7 talking about optimization. So I would like to just start out by reviewing just what are our steps that we have for optimizing. If we're given some sort of problem where we need to find a maximum or minimum value. So the first step is just try to understand what the problem is asking. Maybe draw a picture, some situations that may help. After that, what do we do? Well, we need a lot of times some sort of formula. That's like, for example, some problems talk about rectangles, so you have formulas like area of a rectangle or perimeter of a rectangle. Versus other problems, as we're going to see today, there's just inherent formulas that you could guess based off of the problem. You also need some sort of notation, right? When we're talking about, say, area equals length times width, what do I mean by the length and the width? Like, what dimensions are that? If I know that, this is a 5 by 11, for example, rectangle, a lot of times we'll say the length is 11 and the width is 5. So it's that sort of acknowledgement of what are our variables. Okay, so what else? Well, we need it to be some sort of formula that only has one variable. Right? In our area equals length times width, we have length as a variable and width as a variable. So often we'll come up with a second equation to solve. To get it in the required way that we want it. Then we maximize or minimize. It's your standard first derivative test. And lastly, we find the quantity that we need. Right? Sometimes it will ask for what's the area of this thing. Sometimes it will ask for what's the dimensions of this thing. Depends on the situation. So let's just do one example. Suppose we have a rectangle with a fixed area that has the smallest perimeter possible. What are the dimensions? Well, I see the word smallest, and that means a minimum, which means it's an optimization problem. So I could start out by drawing. I have a rectangle. My area inside is 1,000. And I want to minimize perimeter. So if I call this length and this width, that's our notation. You have two formulas that you can come up with. First of all, perimeter, you add up the sides, so there's two of these lengths. So 2L plus 2 of the widths. Okay, but that has two variables in it, so we need another one. Well, we know that the area of a rectangle is the length times the width, and this area we know is 1,000 meters squared. In other words, our width is 1,000 over L. So we can take that and plug it into our perimeter equation, give us 2L plus 2,000 over L. Just by plugging in 1,000 over L for W. And now that's all in terms of one variable. You have L on one side, this L on one side, and the other is just P. So we can maximize this by taking first derivative. You get 2 minus 2000 over L squared. And we look for the critical numbers. Well, you have a critical number 0. That one's not super helpful because look, length is undefined at 0. But when you have no length, it's not going to be a rectangle. So that's not a feasible answer. So you set this equal to 0. So 2 equals 2000 over L squared, or 2L squared equals 2000. That is, L squared equals 1000. So then, what is L? Well, as it turns out, so this would be square root of 100 times 10, right? 1000 is 100 times 10. Square root of 100 is 10, so this is 10 root 10, which, just to get a sense of what that is it's approximately 31.62. So we could check this. 10 root 10, and make sure that this is a minimum. So L equals 10 is less than it, and L equals, well, let's say 40 is greater than it. You're just plugging that in to 2 minus 2000 over L squared. And you'll get negative 18 when L is 10. And when L is 40, you get a 0.75, which is positive, which means this is a minimum. And again, you could check the sort of like endpoints to be sure it's absolute, but 0 is not going to intuitively make sense. So that means having a length of 10 root 10 is what gives us this. But it asks for the dimensions. That's not just the length, that's also the width. So what is the width? The width is going to be 1000 over 10 root 10, plugging in L. So then that's going to be 100 over root 10, or 100 root 10 over 10, just rationalizing quickly, is also 10 root 10. So, in conclusion, when we have this, our dimensions to have the smallest perimeter possible is a square with, it's a 10 root 10 by 10 root 10, which is approximately 31.62 by 31.62 meters squared. Okay. So that's one example. And sort of similar to what we did previously. So let's do one that's a little different. Find two numbers whose difference is 100 and whose product is maximum. Okay, So there's no picture to draw. So we need to just understand first notation, because there's nothing we can really draw. It's talking about numbers and these operations. So let's call them x and y. And their difference is 100. So difference means subtraction. And their product, which is multiplication, is maximum. So I'll call it m for multiplication of their product is going to be x times y. And then their difference, which is x minus y, or you could do y minus x, equals 100. Okay. So that's what we have to work with. Now this has two variables in it. It has x and y on the right. So we could take this formula and solve. X equals 100 plus y. So m is equal to x times is, I apologize. It is equal to 100 plus y times y, or 100y plus y squared. Okay, and we said we want the product to be maximum, so we need to optimize that by finding its extreme value. So we start by finding critical numbers. It's a polynomial. It's going to be defined everywhere when we take its derivative, which is 100 plus 2y. So we just set that equal to 0 and solve. 2y equals negative 100. Y equals negative 50. So in that case, we can check this. Negative 50. And what do we get? Well, we could try numbers less than. So let's say negative 100 and numbers greater than, so 0. You take the derivative. You plug this into the derivative. What do you get? Negative 100 plus 2 times negative 100. It's going to be negative. And if you plug in 0, you get positive 100. So this is minimum. So that is negative 50 is going to be our minimum value. Okay. So what is x then? Well, it's 100 plus negative 50, or just 50. So our two numbers are 50 and negative 50. And that is another example, is doing these sort of working with numbers, not something geometric. So tomorrow we will do a couple more examples to finish off this section. So I will see you then virtually.